This lecture will be over Chapter 19, Section 4. We're going to discuss energy and power in electric circuits. So a circuit element is going to have a particular potential difference V and a current I, and it's going to put energy into a circuit if the current direction is from lower to higher potential in the device. And it's going to take energy out of the circuit if the current is the opposite. The power rate of energy transfer is going to be the voltage times the current. A resistor always takes energy out of the circuit, converting it into thermal energy at a rate given by power is equal to the voltage times the current. And then you replace the voltage there with IR until you can see the I squared R develop. Or you can rewrite that as the voltage squared divided by the resistance, depending on what information you might have at that particular point. So let's say you got a box here, and we're going to label it current element or circuit element, just simply because we don't know what it is. But it's got some sort of potential difference between its terminals and some sort of current passing through it in the direction from A to B. It could be a resistor, it could be a battery, it doesn't matter. So a charge passes through the current element, and the electric field does work on the charge. So when the charge, Q, passes through the circuit element, the work done on the charge is going to be equal to the product of Q and the potential difference. When that potential difference is positive, a positive amount of work, or Q times V, is done on the charge as it falls from potential VA to VB, from a higher potential to a lower potential. If the current is I, and then at the time interval delta t, the amount of charge that passes through is just basically our definition of current rewritten. So the amount of work done is going to be the voltage times a change in charge is going to be equal to that. This work represents electrical energy transferred into the circuit element. The time rate of energy transfer is going to be the power. In other words, the amount of work done you do in the amount of time, just like it was back in Physics 1. That's exactly the same type of definition here. And the power is going to be denoted by P. Dividing the preceding equation by delta T, we obtain the time rate at which the rest of the circuit delivers electrical energy to the circuit element. So you can see our definitions here. So remember that if the power delivered to a circuit element is negative, then the element is acting as an energy source, delivering electrical energy to the rest of the circuit. For a battery, you might imagine, it's going to convert chemical into electrical energy and delivers it to the external circuit. When current flows through a resistor, electrical energy is transformed into thermal energy, heats up. Electric toaster is a good example. We're going to calculate the power dissipated through a resistor as follows. Potential difference is going to be V is equal to IR. The electric power is going to be represented by the formula we went over in the summary. So what happens to this energy? The moving charges collide with atoms in the resistor and transfer some of their energy to these atoms, increasing the internal energy of the material. Either the temperature of the resistor increases or there's a flow of heat out of it, or both. In other words, we say the energy is dissipated in the resistor at this particular rate. If the temperature gets too high, it can change the resistance unpredictably, and you may end up with a melted or exploding resistor. You probably don't want that in most cases. Some devices, such as electric heaters, are designed to get hot and transfer heat to the surroundings. In other words, that's what you want. But every resistor has a power rating, maximum power that the device can dissipate without becoming overheated and damaged. In practical applications, the power rating of a resistor is often just as important a characteristic as its resistance. So let's take a look here at this particular situation. We've got an EMF source here that converts non-electrical to electrical energy at this rate. Its internal resistance dissipates energy at this rate, and then the difference is going to be the power output. So the upper box is going to represent a source with EMF and internal resistance R, connected by ideal resistance-less conductors to an external circuit represented by this box. This arrangement could describe a car battery connected to the headlights. Point A is at a higher potential than point B. You can see that in both cases. But now the current is going to be leaving the device at a higher potential terminal rather than entering. The energy is being delivered to the external circuit and its rate of delivery is going to be given by this equation right here. For a source that can be described by an EMF and an internal resistance, we can use this. So one possible configuration of something like that is where you've got a battery that's hooked up to a headlight and the battery supplies the voltage potential difference there for the headlight to operate. So, got a few examples to work through there.